Hello, I'm Hiroyuki Katsura from University of Tokyo, and today I'm going to talk about a new refinement type system for automated nu-HFLZ validity checking. And this is the joint work with Naoki Wayama, Naoki Kobayashi, and Takeshi Tsukada. And the purpose of this research is to create an efficient automated validity checker for nu-HFLZ. The reason why we focused on nu-HFLZ is that it has a lot of applications. First, it gives an uniform approach to functional program verifications. For example, Kobayashi and others have proved that a safety property problem of higher order functional programs can be naturally reduced to HFLZ parity checking. And also, if you are familiar with constraint home clauses, our work is considered to be the higher order extension of CHC-based program verification. And secondly, nu-HFLZ validity checker is considered to be a building block of full HFLZ validity checker. And Kobayashi and others have proposed a solver for full HFLZ validity checker, and in their solver, they intensively utilize nu-HFLZ validity checker repeatedly. So, in that sense, for the efficiency of full HFLZ validity checker, an efficient automated nu-HFLZ validity checker is desired. Okay? So this is the motivation for our work, and our contribution is that we propose a new refinement type system with precise subtyping rules for nu-HFLZ, and also we implemented an automated variety checker for nu-HFLZ based on our proposed type system, and finally we evaluated our type solver based on some benchmarks taken from some higher order functional programs. And before we dig into the detail of refinement type system, we like to review nu-HFLZ and its application. And nu-HFLZ is proposed by Kobayashi and others, and this is considered to be HFL plus integer minus least fixed points, where HFL is the higher order version of fixed points logic. And let us see the syntax below. And the first three lines are typical logical components, and the fourth line is related to higher order predicates. So we can define lambda abstraction and application in the logic. And also notable point of this logic is that we can define greatest fixed points in the logic. So new x point psi here is that means that greatest x such that x equals psi. And in the final line, there are the syntax for integer arithmetics. So we can define and write a property on integer arithmetics in that logic. And below, there is an example of nu-HFLZ. And this is the first order formula. And it takes an integer y and checks if y is not equal to 0 and xy plus 1 holds. And as you may notice that this formula is defined by the greatest fixed point. So the meaning of this formula is the greatest x such that this equivalence holds. And as I explained in the next slide, this formula is equivalent to y is greater than 0. So let us check the meaning of this formula in more detail. As I mentioned in the last slide, this is defined by greatest fixed point. So formally, the meaning of this formula is the greatest solution of this equation. But to understand intuitively, we would like to guess the meaning by unfolding this equation for several times. So this part, there is a fixed point, so we can expand it once like this. So we now have n not equal to 0, and still there is a fixed point. And we can continue this operation. And now we have n is not equal to 0, and n plus 1 is not equal to 0, and it's almost the same formula. And we can continue this procedure, and we have now, you may guess that for the positive integer n, we will not falsify by any part of this not equal 0 part. So for the positive integer, this formula will not be falsified. So in that case, in the same context of greatest fixed point, we can say this is true. So this formula is equivalent to n is greater than 0. This is the intuitive meaning of greatest fixed point. And I would like to talk about the application of nu-HFLZ before we start our work. Kobayashi and others have proved that, as I mentioned, safety property problem of higher order functional program can be reduced to nu-HFLZ validity checking. And for example, consider this program. This is an OKML program, and some function takes an integer x and continuation function k and calculates the summation from 1 to x and then passes the result to k. And in the main function, it takes an arbitrary integer n and passes the integer to sum and check if the result of the summation is greater than or equal to n. And so this problem, by using the Kobayashi and others reduction, the problem check whether this assertion never fails or not can be reduced to the following nu-HFLZ validity checking problem. And the reduction maybe can be understood in a straightforward way. There is some cross correspondence. For example, some function can be reduced to the predicate defined by greatest fixed point like this, and the body part is like this, and also main part is also has a cross correspondence. And now we'd like to have an automated validity checker for nu-HFLZ. Then if there is such an efficient solver for nu-HFLZ, then we have now safety property problem solver also. Okay, so we'd like to create such solver for nu-HFLZ. So how to do that? To do so, we propose a refinement type system for nu-HFLZ. So let's talk about that. The syntax of refinement types is like this. The notable point of our refinement type is that there is a refinement constraint for Boolean type. And the semantics of this type is that type of propositions that hold whenever theta holds. So, for example, for this formula, x is not equal to 0 has type x is greater than 0 because x is greater than 0 implies x is not equal to 0. And for higher order cases, this is the type of higher order predicates, and the meaning is a little bit standard type of higher order predicates that return type tau 1 when they take a formula of type tau 1. Returns the type tau 2 when they take a formula of type tau 1. And for example, for this formula, it takes a predicate p and then applies p to 0, and the formula has this refinement type, because if p has this refinement type, then in the body of the formula, it always applies p applies to 0, so that it always true. We can say it's always true. And type judgment is a standard one. It's a triple of type environment, formula, and refinement type. But subtyping judgment is a little bit strange, has a little bit strange part here. And this is a constraint formula, and the semantics of this subtyping judgment is that in type environment delta, if constraint theta holds, type tau 1 is a subtype of type 2. And for example, this is a valid subtyping judgment because in the context of n is greater than 0, this subtyping holds. Okay. And here are typing rules and subtyping rules. And I'll pick 3 rules from typing rules. This is a rule for conjunctive formula, and it is a straightforward rule maybe, because if we assume psi1 has type theta 1 and psi2 has type theta 2, Then the conjunction of psi 1 and psi 2 has type theta 1 and theta 2. And for the greatest fixed point, we have this rule. And to prove the greatest fixed point, psi x point, nu x point psi has type tau, we assume x has type tau and then prove psi has type tau. And finally, we would like to introduce you a subsumption rule. And in the subsumption rule, we utilize subtyping rules below. And the model point of it is that here we only consider that constraint formula holds. So for the Boolean type, we generate these constraints to check if this subtyping is holds. And also, here is the strange map. And this is the main contribution of our work. So we would like to talk about this RTY constraint in the next slide in more detail. And this is the proposed subtyping rules for higher order cases taken from the last slide. And I'd like to talk about what is RTY constraint and why it is important. And RTY is a map from refinement type to constraint formula theta, and it extracts the constraint of the result type. So for example, for this refinement type, we pick this n is greater than 0, so the result value of this function called is n is greater than 0. And the reason why we consider this RTY assumption is that this assumption has a great impact on the probability of the refinement type. And to illustrate this improvement, we would like to talk about this example now. And this subtyping is taken from the derivation tree in the some validity checking of some example in the introduction slide. So to prove the some example in the introduction slide, we have to derive this subtyping. And because this is the higher order case, we apply this rule now. And to apply this, to proceed with this rule, we pick this result assumption here and put it here, and then continues to this to applying subtyping rules. And finally, we reach the Boolean case and check if this constraint holds by using SMT solver. And the important thing is that without this assumption, this constraint does no longer hold. So, at least in this case, the assumption of RTY is necessary. And as we will later confirm in the experiment section, the existence of RTY assumption is very important in the efficiency of the resulting solver. And now I'd like to understand why we consider assumption RTY. Maybe you may consider the subtyping rule for higher order cases like this, but we choose this one. So why? So to understand this RTY, we would like to consider the case where RTY tau is false. And in that case, tau means that all the formulas. So tau is going to be a bottom when the RTY tau is false. So in other words, when the RTY tau 2 doesn't hold, this subtyping trivially holds. So we don't have to care about that. So it's enough to consider only when RTY tau 2 holds. So we have this. And in fact, this assumption is theoretically important because now, thanks to this subtyping rule, we have soundness, but not only soundness, but also completeness property of the subtyping rule. This is the main theorem of this paper. And also, we have, of course, soundness property, and as a corollary, we can say that this type system is useful for nu-HFLZ like this, by using like this. And now we would like to compare our work with the previous work done by Ban and others. And also, their type system is targeted for satisfiability of higher order constraint Hom clauses. But as I mentioned before, satisfiability of higher order constraint Hom clauses is the dual problem of validity checking of nu-HFLZ. So we can consider the dual type system from the Ban's type system. So we can consider their type system as a type system targeted for nu-HFLZ variety checking. And then we can compare their work and our work. And our type system is inspired by and closely related to their type system. However, our type system is more expressive because thanks to our sophisticated subtyping rules, as I mentioned, as I explained so far. And the important theoretical gap between our work and their work is that their subtyping rules are not relatively complete. And in practice, this difference is very important in the solvability of the resulting automated variety checker. And yeah, as we will confirm in the experiment section. And before we consider the experiments, we would like to explain type inference method. And I think this type inference method is a little bit standard, and we adapt template-based algorithm based on refinement type system. And to illustrate our algorithm, we consider this example, and especially we focus on this part. And our algorithm is divided into 4 parts. And first, we infer a simple type of the given formula in a standard way, and then create a template and based on the simple type inferred in the previous step. And importantly, we have to make sure that all the predicate variables can depend on appropriate variables. So for this part, we can depend on these 2 variables. And then next, construct a type derivation based on the proposed refinement type system. And in every time we apply subsumption rule, we can collect constraints on predicate variables. So for example, for this example, we have this constraint. And then now we have a set of constraints. So all we have to do is to solve these constraints to check if the whole derivation is valid or not. And we'd like to talk about this constraint solving part. In general, the shape of the constraints looks like this one. The conjunction of predicate variables and theta, which is the constraint formula, implies the disjunction of predicate variables. So, and to illustrate the situation, we would like to divide the cases into 2 parts. First, if the constraints contain disjunction at the head, we use PCSAT. And otherwise, and in this case, it is called constraint Hom clauses. And in that case, we can use CHC solver, which is there is a sophisticated CHC solver. So we will be happy if we can utilize this solver. So what case do we reduce the problem into CHC constraints? Now, I would like to analyze this part. And one thing that I can say here is that for variety checking of nu-HFLZ reduced from safety property problems, the generated constraints will be no longer contain disjunction at the head of each clause. So in such cases, we can solve the instance by CHC solver. But how about other cases? And to consider these other cases, we call these kinds of nu-HFLZ formulas conjunctive nu-HFLZ formulas. And then recently, Asada and others have proved that order n nu-HFLZ formulas are reducible to order n plus 1 conjunctive nu-HFLZ. So by using their reduction as a pre-process, we now we are able to reduce all the constraints to CHC solving. Now we would like to report my experiment results. We implemented our solver, and we called the solver RESTful, and we utilize benchmark taken from safety property problems of higher order programs. And we compared our work with Horus, which is the proof of our concept developed by Ban and others. And also we compared our work with Powerful, which takes a little bit different approach from ours based on predicate abstraction and counterexample guided abstraction refinement. And compared with Horus, our solver can solve more instances than Horus, and this is expected because thanks to our sophisticated subtyping rules. And compared with Powerful, our solver can solve instances more quickly. And in theory, Powerful can infer intersection types. So in that sense, their solver is more expressive, and so our solver and their solver can consider to be complementary. Finally, I would like to talk about related work. The main related work is Ban and others' work. And from the experimental results and also from the analysis of technical things, our solver can solve more instances than theirs. And compared with another approach, a model checking based approach, from the experiments, our solver can solve more instances more quickly. To conclude our talk, we summarize our work. We proposed a new refinement type system, and as I explained, the subtyping rules are not only sound but also relatively complete. And we also implemented an automated parity checker, and experiments show its effectiveness. And as a future work, it still suffers from incompleteness problem. So to improve this situation, we have to invent another type system and inference method. And that's all. Thank you for listening.
Thank you very much. Any questions?
So how does your approach compare to like more used refinement types of verification like S star or liquid types?
So for example, as for xFSTAR, it would require to annotate refinement types, but our work is not required to write some refinement types before the verification. So users don't have to write any refinement types for this approach. So I guess this is the main difference between xSTAR and our approach.
And in terms of scalability?
Sorry?
In terms of scalability?
Scalability. Scalability problem is, yeah, of course, post can happen, and yeah, this is in some sense well, of course, problematic. It can be problematic, and yeah, and it can be solved of course, modular verification can be a future one, I think. Thank you for
Any more questions? Okay, let's thank the speaker again.